Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at section 1.4, which is on inverses and algebraic properties for matrix operations. And today, we are also going to use this opportunity to give you a very gentle introduction on how to write mathematical proof, which is required in this course. And we are going to start looking at how do you make a very simple mathematical argument by following very closely on the mathematical definitions. So we are going to look at a lot of examples like that in this video. So let's get right to it. All right, let's first look at the objective for this particular section. So at the end of this section, you should be very comfortable with the definitions of invertibility of a matrix. And more importantly, you should be able to use these definitions to find the inverse of a specific matrices. Okay, so before we get to matrices, let's do a very quick review on some of the properties for real numbers. We all know that 0 has these particular properties, and having these properties will qualify 0 as what we call additive identity. And we also know 1 has these particular properties, and having these particular properties will qualify 1 as what we call a multiplicative identity. So obviously, as you can see, when we do additions, 0 have this particular very nice property. And when we do multiplications, the number 1 has this very nice property. And this property can be extended to matrices as well. I'm saying that matrices also have this kind of property. So for example, the 0 matrix, this is what we call a 0 matrix. 0 matrix is the additive identity in the matrix operations, matrix addition operations. So as you can see, you have matrix A plus a 0, you get back the matrix A itself. And again, this is just an example. This is because not all matrices is going to be of size 2 by 3. So in general, a 0 matrix is a matrix of any size where all their entries are zeros. And the corresponding concept for the number 1 is in matrices is what we call the identity matrix. So identity matrix is written as I and is a square matrix. So this one is a little bit different. 0 matrix can be of any sizes, but identity matrix will have to be square matrices, so n by n. So like say 2 by 2, 3 by 3, so on and so forth. It has to be a square matrix. Where the diagonal of this matrix are all 1. So this is a diagonal matrix, and everything that's off diagonal, they are all 0. So for example, this is a 3 by 3 identity matrix. And so it behaves kind of like the number 1 in the number system. So this matrix, multiply this, will equals to that original matrix. And you can do it from the left or from the right-hand side. So identity matrix is what we call the multiplicative identity in the matrix multiplications. Okay, so we also have the concept of the additive inverse. So additive inverse for numbers is the number that is like this, so they have this property. And for every non-zero numbers, we also have something called a multiplicative inverse. So multiplicative inverse is something that looks like this. So for example, 2 has a multiplicative inverse. The multiplicative inverse is 1 over 2, so that the product will give you the number 1, which is our multiplicative identity. And this is the same as if you take 1 over 2 times 2, right? So this kind of things works as long as this number here is not 0. So if you have non-zero numbers, you definitely will have the multiplicative inverse. And this is also notation-wise, this is something that we write like this. So for matrices, having an additive inverse is pretty straightforward. So for matrix A, the additive inverse is like this, right? That's pretty straightforward. And the multiplicative inverse is a concept that we want to talk about, which is the inverse of a matrix, right? So the multiplicative inverse is something that looks like this. So we're going to go give you the definitions for a matrix that is invertible. So again, first of all, being invertible for matrix multiplication will require the matrix to be a square matrix. That's the first thing we need to know. So let's say your matrix A is a square matrix, which is say of size n by n. So this is sometimes is how I write. You will understand, comprehend more about this notations and later on, but I can write like this. I can just write it out like A is of size n by n, right? So A is a matrix of size n by n. And if you can find another matrix B of the same size, so B is also n by n, so obviously square, such that A times B will equal to the identity matrix, will equals to B times A. If you can find that matrix B, so if matrix B exists such that you have this property, then we will say matrix A is invertible, okay? Has inverse, invertible. Another way of saying it is to say that matrix A is non-singular, and the matrix B is what we call the inverse of A. So notation-wise, we will also write B as A inverse, okay? So, and if no such B exists, if you can't find such a B so that this is true, then we will say that A is not invertible, or also referred to as a singular matrix. Okay, so this is nothing but the analog of what happened here for numbers. So for numbers, okay, if you have a non-zero numbers, you will be able to find the multiplicative inverse. So that is something that you multiply to it will equals to 1. Right, so for matrices, the 1 will be our identity matrix. So that's the reason why for the definitions, you are looking for a matrix B so that this product will give you the identity matrix, just like the number 1 in the number system. And as you can see, if you compare here, we want it to we want this multiplicative inverse to be on the right hand side and also on the left hand side. So that's the reason why we want it to have a B, so that this B multiply A on the right hand side, or this B multiply A on the left hand side will give you the identity matrix. If you can find such a B, then we will say that A is invertible. It's invertible. It has an inverse, and the inverse is B, right? So the inverse is B. So look at this. That's kind of like your B. This is your A. That's your B. Okay? So that's the definitions for a matrix to be invertible. Okay, and if A is not invertible, we also call that matrix A is singular. Okay, so just by definition, we are not talking about any formulas. We are not talking about algorithms to compute the inverse. We're not talking about all that in this particular videos. We are just going to follow this definition. So everything will be just following this definition. So using nothing but this definition. So some of you already know the formulas to compute inverse. Some of you know fancy terminology like determinant and all that. So we are going to resist the temptation of using all this idea. If you have seen it before, we are not going to use all that. We're just going to concentrate on the definitions of the invertibility of a matrix. And now I'm asking you these questions. All right, is this following matrix invertible or not? Okay, so my question is this matrix invertible or is it not invertible? And you will have to answer these questions without using any formulas, just using this terminology. And I want you to give this a thought, okay? And let's pause this a little bit and give it a little bit thought and see how you're going to approach this particular problems if you can't use any formulas but the definitions. Okay, let's give this a little bit thought. Okay, so I hope that you come up with a strategy of identifying the solutions for this particular problem. So what we do, since the only thing we can do is to use the definition, so let's try to find a matrix, all right, and see whether or not you can find such a matrix so that this matrix, okay, multiply with this will equals to the identity matrix. So the identity matrix here is our 2 by 2 identity matrix. So if you can find such a matrix so that this product is equal to I, and if you switch this around, you can also still get I, then we will be able to say that this matrix is the inverse of this matrix. But if you do it like this, okay, if you set this thing up, you will see that this is require us to have 1a and 2c equals to 1. That's how you get these equations. And then we also require us to have 2, 4, and ac equals to 0, right? So this is matrix multiplications, 2a, 4c equal to 0. And then we will have to have this equals to 0. That's give you the third equation. And then we will have to have this equals to 1. That gives the fourth equation. And if you set this thing up, try to solve for A, B, C, and D. So you try to solve for it. So this is our A, B, C, and D. So encode this system of linear equations into this augmented matrix and row reduces it. You get all the way to here. And as you can see, this is our pivot, this is our pivot, and this is the one that tells us that there's no such A, B, C, D. So this system is inconsistent because there is no such A, B, C, D that will satisfy all these requirements. So this system has no solutions. Therefore, there's no way you can find a matrix that can do that. So by the definitions, no such matrix exists such that A, B equals to I. So by definitions, this matrix is not invertible. So as you can see, we are not using anything but the definitions to figure it out that this matrix here is actually not invertible. Okay, so it's not invertible. Okay, so this is how you apply definitions. Okay, so for example, if you are given a matrix A and a matrix B, and you are asked to, if you do these computations, you will see that AB and BA will both give you this identity matrix. You multiply A and B together, you get I, you get B and A, you also get I. So by definitions, this matrix here is the inverse of this matrix. All right. So we have AB equals to I equals to BA. So this matrix B here is the inverse. Okay, it's the inverse of A. We don't know how to obtain that, but apparently if we just do this computation, we realize that that's I. And we do this computation, we realize that that's I. So by definitions, this matrix B right here is the inverse of this matrix A. Okay. So let's continue our discussions. Now things are getting a little bit more theoretical. And so this is probably the first time when we talk about theorem in this course. So the questions here is that whether or not the inverse, if you found the inverse of a matrix is can you find another one? Right, so let's say that this is a matrix A, you found a matrix B such that you have this property. Can you find another matrix C, okay, of size 3 by 3, such that AC will also be equals to I and equals to CA? So the question here is whether or not the inverse, if you found them, okay, is this the only one? So is this the only inverse for your matrix A? All right. And the theorem here says that it is. The answer is that the inverse of a matrix, if it exists, it will be unique. All right, it will be unique. And the way they say it is that if you can find B and C both are the inverse of A, then B and C is actually the same matrix. That's another way of saying that inverse of a matrix, if exists, has to be unique. All right, so let's look at the proof. Okay, so how do we actually prove a theorem that looks like this? So a theorem consists of hypotheses. So theorem always start from if something and then the conclusions. All right, so the theorem is always started with the hypothesis. These are all the assumptions, and then that is the conclusion. So the assumption is that the B and C is the inverse of matrix A, and the conclusion is that those two matrices B and C are the same matrix. Okay, so during this proof, we are going to use a lot of these hypotheses, the assumptions that the B and C are inverse of matrix A. All right, and this is what we want to show at the end. Okay, so let's take a look. So suppose B, by hypothesis, that it is the inverse of A, then we must have this. Okay, so BA must be I. Obviously, AB is also I, but I'm not using that direction yet. I'm just saying that, oh, okay, BA is I. So if I multiply this equations by C, I'll multiply everything on the right-hand side, and I will get that. And matrix multiplication is associative, which means like for numbers, 2 times 3 times 4 is the same as 2 times 3. First then times 4 is also the same as 2 times and then 3 times 4. This is called the associativity of multiplication. And this kind of associativity properties also hold for matrix multiplication. So which means the ordering doesn't really matter. So once you get to this, I can look at this multiplications, and let's do AC first. So I have BA equals to I from hypothesis. I multiply C across. That's what I get. That's my equation 2. And then I am using the associative property. So instead of doing this bracket, I am going to do this operation first. And AC is an identity matrix. You know why AC is an identity matrix? Because the hypothesis say that C is an inverse of A. So C as an inverse of A means that AC is I is equals to CA. So by associativity, by looking at this part first, we get this is I. So identity matrix has this property. So B times I is equal to B. So you can see the second equation here, BAC give you C, and the third equation here give you BAC equals to B. So BAC equal to C and BAC equals to B, that will force these two matrix B and C to be the same. So this is a very simple mathematical argument to show that matrices, if they have inverse, the inverse are unique. You can only find one matrix to be the inverse of another matrix. If you can find another one, that another one is actually the same one. That is the way we say that matrix inverse, if it exists, is unique. And you can see the proof. This is a kind of proof that you are going to study and be able to write at the end of the course. This is a very simple proof utilizing very simple arguments and basically just using the definitions, nothing more than using the definitions and to make an argument that is like this. So this is like the first time you see theorem for this course, and this is also the first time you see a mathematical proof in this course. And this is we try to do a very gentle introductions on how to write proof for a theorem. So let me say that again. So a theorem has the hypothesis part, and then we'll have the conclusion part. Okay, so as you can see, when we are making the arguments, we're using a lot of the hypothesis. Okay, and then we'll try to reach the conclusions, which is right here. Okay, so next theorem. Okay, again, this is a theorem. Will be something that will have the hypothesis. So we have stated the hypothesis if what, and then the conclusion will be something. Okay, so let's take a look. What is this theorem trying to say now? So the theorem says that if your matrix A and matrix B, they are both square matrices of the same size, and also that they are invertible matrices. Okay, so they are invertible matrices. So we are given A and B are invertible matrices. What do we want to show? So we want to show that the product, okay, so your A, B, these are separate matrices, square matrices of the same size, also they're invertible. Then if you multiply them together, this is again a square matrix of size n by n. We claim that this matrix AB, the product, this matrix AB as one matrix, is actually invertible. And the inverse for this matrix is the products of B inverse times A inverse. Is the product B inverse A inverse. So that's what the theorem said. Okay, so that's what the theorem says. Be very careful on the hypothesis and the assumption. So the assumption is that A and B are both invertible matrices. They are invertible matrices, okay, of the same size. Okay, square matrices invertible of the same size. Then the product is also invertible, and actually you are given this particular formulas right here. The inverse of AB is B inverse times A inverse. So how do we prove that? Very straightforward. So if you want to show that matrix AB is invertible, you will have to find something so that the product is I, and you have to make sure that that something multiply AB on the other directions will also give you I. How do you know that? That's definitions. So definition says that if you can show this, if you can find a matrix such that you have that property, then this matrix AB is invertible. And what is the inverse? The inverse will be this. Okay, so if you can find this matrix right here, okay, a matrix right here such that you have this property 1 and 2, then AB will be invertible, and the inverse is actually that thing right here. Okay, that thing right here. Okay, so what we do is that since we've been told that that is our inverse, so we are going to very conveniently put this matrix right here and compute. So matrix operation is associative. So instead of doing this operation first and then do this operations, I can choose to do this operations right here. And B inverse make an identity matrix. That's identity matrix will make this equal to this. And by definition of inverse, multiply the matrix itself, that give you I. So we have shown AB times this equals to I. Very straightforward, using nothing but the associativity property for matrix multiplication. So let's do that one more time. Put this thing right here on the left-hand side of AB, and again, use the associativity property and also the inverse property. We get this to I, and then here we get this to this, and this is this. So we have found a matrix. Okay, so we have found a matrix such that this matrix multiply AB equal to I, and this matrix here multiply AB equals to I. So the inverse, okay, of this matrix is this thing right here. So that's the B inverse and A inverse. So we know, so now we know that if A and B are both invertible, their product is also invertible, and we have a formula for the invertibility, the inverse of AB. Okay, so that's that. So again, you can see this is a very simple theorem. Theorem consists of the hypothesis and conclusions, and we can see the proof is also pretty straightforward, utilizing nothing but the definitions of the theorem, the definition of the invertibility of a matrix. Okay, all right. So that's very good. That's how we complete the proof of that particular theorem. Okay, I want to give you another example before I ask you something more complicated. So, so suppose we are given a matrix A. So as you can see in this video, we are not using any special formulas to compute inverse whatsoever. We are just using the definitions, okay? So now, this is also something that is very interesting. So you are given a matrix A is of size n by n, and it says that you take this matrix, you square them. Square them means that you A times A. And then you take 5, scalar multiply them, and you have identity matrix, scalar multiply this with -7. And it so happens that if you do this computation, you will have a 0. So this 0 here is not the number 0, but it's a 0 matrix. So it's a matrix of size n by n, where all their entries are 0. So this is the concept of a 0 matrix. So this is a 0 matrix. Okay, so it says that if you have a matrix A, size n by n, and if you do these computations, it equal to the 0 matrix, then they ask you to prove that this matrix A is actually invertible. So again, if you want to show that this matrix A is invertible, by definition, you will have to find a matrix, another matrix, such that this product equals to I, and make sure that this exact same thing right here, if you multiply A, will also give you the identity matrix. So we want to find this. This is what we want to find. Okay, so this is what we want to find. Oh, by the way, WTF in this course is one to find, not the one that you're thinking about. Okay, so that's what we want to find. Okay, so from this, we will be able to move the -7s to the other side. That's totally okay. I can factor out an A, so you can factor out an A that looks like this. And again, when you factor out A though, so you have A squared plus 5A. When you factor out A, please do not do this, because this would not make sense, because this is an n by n matrix. N by n matrix, you cannot add it with a number, remember? So the way when this factorization happens, this is supposed to be 5 times I, not just 5, okay? So this is one thing that is undefined. You can't have A plus 5. So this is an n by n matrix. You can add an n by n matrix by a number. Okay, all right, so this is going to be 5i. Okay, remember, this is how you factorize, and then you can divide, or you can think of it like scalar multiplying 1/7 across, so you get that. So this is what happens. You have A and then times this matrix. This is again an n by n matrix. You get I. And if you go back to this equation and factor the other way around, so instead of taking the A out this way, you take the A out this way, and again do the scalar multiplication of 1/7, you will see that this is also true. So you will see that A multiplied this equals to I, and we'll see that A multiplied this equals to I. So again, by definitions, what is the inverse? The inverse exists. The inverse will be that thing right here. So that is how you show that the A is invertible, and the inverse for that matrix is actually this. Okay, so again, this is a very simple example that utilize nothing but the definitions. Okay, nothing but the definitions. Okay, so we're going to practice on actually how to use nothing but the definitions of matrix inverse And to answer all these questions, it's a little bit different. It's a little bit more abstract, and that's the problem with this particular course here. This course is going to get pretty abstract at the end, in the middle, and is usually sometimes students having a hard time transitions because things is a little bit different. This is not like calculus, differential equation where you just differentiate and integrate. It's very computational, but not for this one. This one can be very conceptual, and this is the conceptual part of the course where we try to deal with. This is a very gentle introduction, so we'll get more complicated at the middle of the semester, but this is critical, and I want you to pay a lot of attention to how we actually make a mathematical argument. All right, so I want you to look at these questions and give this a little bit thought. So suppose that we have matrix A and B. They are all square matrices of the same size, and we've been told that the product is invertible. Okay, all right. So what you need to do is to show that matrix A is invertible, and actually also B is invertible. But let's just do one of it, right? Let's just do one of it. So, all right. All right, I'm going to suggest that we pause this video for a little bit, and so that we can give this problems full considerations. And once you think you have the answers, you can get right back to it. All right, see you very soon. Okay, welcome back, and I hope you already have your answers. And the reason why I want you to write down your answers is because I want you to learn from your mistake if you have a mistake here. And usually this is a questions where students make a lot of mistakes, because in their argument, they will be using AB inverse equals to B inverse A inverse. So if you have something written down like this, then you are wrong. I'm sorry to say that, because you get yourself confused with the previous theorem. So again, be very careful when you use a theorem. So when you use a theorem, you have to know that the hypothesis of a theorem has been satisfied, because, like, for example, in this case right here, you have a theorem which says that if your A and B are known to be invertible, then the products of AB is invertible, and that's the formula for the invertibility of the matrix AB. But the hypothesis is that both A and B are known to be invertible. And you can't really use it in this particular problem here, because you are asked to show that A and B are invertible. You do not know firsthand that A and B is invertible. So if you use these formulas, then you will get 0 out of 10, because you are very confused about the type of theorems that you're using and the hypothesis of a theorem. So you are actually being asked to show that the matrix A and B is invertible without knowing beforehand that they are invertible. So applying the previous theorem will get you into very big trouble. So how do you actually solve a problem like this then? So we know that AB is invertible, and your job is to find is to show that the individual matrix A and the individual matrix B is also invertible. So to do that, we will have to find, okay, so we'll have to find something that multiply to A and equals to I, and we'll have to find that something and multiply A and equals to I. If you can do that, again, just by definitions, we will say A is invertible. So you have to do the same thing for B. You have to find something that multiply B is equals to I, and you have to find that something that multiply B is equal to I. And if you can do that, B is invertible. Okay, so nothing but the definitions. Okay, don't do anything that you're not allowed to do. And before we do that, I want to introduce you another mathematical facts that sometimes showing this part is easy, but showing this part is difficult. But just good news is that if this is an n by n matrix, and this is an n by n matrix, and this is an n by n matrix, knowing this actually is enough, because knowing this will implies that this will be true. And knowing this will imply that this will be true. So actually, we don't have to do this two process. We just have to do one of it. If you have one of it, you have another one. Okay, so that is given as the lemma right here. So lemma is a theorem. It's not a big theorem. It's a theorem that helps us just to get some bigger results. So lemma is the name. So lemma, think of it, is just a theorem that is not so significant. It's just we uses it to help us in getting some bigger result, but we just kind of like just uses it and then throw them away. That's the kind of like the meaning of a lemma. So here it says that if you have two square matrices, and of the same size, if you can show that BA is equals to I, that will implies AB equals to I. That's what it said. Or if you can show that AB is equals to I, then you will have BA equals to I as well. So that's what the theorem is saying. So also hope that you have come across something called if and only if. So if and only if means that it go both sides. It means that if you have BA equal to I, then you will have AB equal to I. And if you have AB equals to I, then you will have BA equals to I. So they go both way. And the theorems, this is a theorems, obviously they will have a proof, so we will skip the proof right here. You can read it. You will read it. The idea is not very complicated, so I don't want to talk about the proof right now. I just wanted to use it. So I want to use it to solve this particular problems right here. Okay, so we will, if we have an opportunity, we'll talk about that in class, in person, during office hour. But right now, I'm just going to make sure you understand the statements of the theorems and of this particular lemma, and I'm just going to use it, okay? So for example, right here, let's back to these questions. So we know that AB itself is invertible. This product is invertible. So this product, AB is invertible, means that I can find something, right? Okay, so and that something here is this is equals to I. So we know that AB inverse exists. So AB inverse exists means that your AB inverse multiply AB will equals to I. So that's the definitions, right? This is the definitions, right? AB inverse multiply AB will equals to I. How do we know that? Because we've been told that the products AB is actually invertible. So we have that. So now you can see if we use the associative property and just compute this, then you will see that B multiply this matrix, B multiply this particular matrix here will give you I, right? This is from the definitions. AB inverse implies, AB inverse exists implies that we have this. And just by using the associative properties, we will see that B times this will equals to I. And from the previous lemma, if you have B, okay, if you have this things times B equals to I, you automatically will have B times this equal to I as well. So what we can see is that B is now proven to be invertible, as simple as that. See that? So same thing right here. So AB inverse exists means that you have this. And using associativity property, if I just do this first, then you will see that A times this, okay, will be equals to I, and the lemma says that this things times A will be equals to I. So I don't have to show both. I only need to show one part of it, and I will have this part's guaranteed. How do you know that? That's what that lemma said, okay? How do you know this lemma is true? Well, you can read the proof. Okay, so as you can see right here, just having AB inverse exists, we know that B is invertible. As just having AB inverse exists, we also know that A is invertible. And again, you can see we're utilizing nothing but the definition. So that is how we are going to roll in these particular sections by doing everything following nothing but the definition. So we make mathematical arguments and get so that we can get the result that we want, but you also have to be very careful about the mathematical arguments that you make, okay? So only uses the hypothesis or the assumptions that you have, and don't confuse yourself with the hypothesis and the assumptions that you have for another theorem where it would not, where it's actually not been satisfied and in other conditions, and you use it anyway. So this is a very simple example that I can give you, which is Pythagoras theorem, right? So Pythagoras theorem says that if you have a right triangle, you have a 3, 4, then you have a 5, right? But the hypothesis for the Pythagoras theorem is that you must deal with the right triangle. So if you do not have a right triangle, you have a 120 degrees right here, and then you have a 3, you have a 4, you can't say this is 5. So this is not true anymore. If you still say this is 3, 4, and 5, then you are making a mistake because you thought this is a Pythagoras theorem, but this is not a Pythagoras theorem anymore. Pythagoras theorem will have to have a right angle, and you do not have a right angle. So this particular part right here is a very common mistake. So you actually really have to be very careful when you use a theorem, okay? You have to make sure the hypothesis of the theorem and the assumption of the theorem has been satisfied before you can draw that conclusions. Okay, All right, so we are going to finish our sections right here, and we're going to stop right here. Thank you. All right, this concludes our lesson for section 1.4, and I hope you learned something today, and I will see you in the next video very, very soon.